Design of reinforced concrete flat slab with drop panels. We have to design the reinforced concrete slab of story 1 of the same structure we are utilizing in the past lectures. We have to first calculate the thickness of the slab. We'll be discussing the thumb rules, how the slab thickness and the code provisions to calculate the initial slab thicknesses. We have to calculate the thickness of the drop panels. We have to calculate the drop dimensions as recommended by the code. We have to design the slab reinforcement. We have to check the slab thickness by the reflection criteria. We have to check the drop thickness by punching shear check. Let's start with the slab thickness as per ACI code. The slab is with drop panels. Starting with exterior panels, we have edge beams, yes. Taking span divided by 36, we get exterior panel thickness as 24 feet span into 12 inches divided by 36 of the formula, we get 8 inches thickness. Now for interior panel, we have LN, that is the clear span, or conservatively you can take the center to center span. And the interior panel thickness comes out to be 24 into 12 divided by 36 is equals to 8 inches. So we'll be defining the slab thickness as 8 inches in ETABS. Now let's calculate the drop panel dimensions based on the slab thickness. It is recommended to use, let's take L1 as the span parallel to the direction of the drop panel having dimension A, and L2 as the dimension parallel to the dimension B of the drop panel. This is the drop panel having a size of A by B, and the span is L1 by L2. So we divide by L1 by 3, giving a drop panel dimension of 8 feet. This dimension is 8 feet recommended by the code, and similarly we have a drop panel size of 8 feet as per the code formula. Thickness of the drop panel is equals to minimum thickness of the drop panel is slab thickness divided by 4, gives us 2 inches. So the total drop thickness is slab thickness plus drop. We get a thickness of 10 inches. Let's define the slab thickness and drop thickness in ETABS. First of all, checking the slab thickness. We already have assigned a slab thickness of 8 inches. While the drop panel we previously assigned of 15 inches. But by the formula we need only 10 inches drop panel. So we'll be revising the slab drop thickness as 10 inches. Make sure you have selected the drop from the list and click on OK. Property modifiers for the slabs using ACI code. In order to consider the cracking of reinforced concrete, we get a 25% of gross moment of inertia. So we'll be defining in ETABS using the slab sections. There are two possible methods of assigning the property modifiers in ETABS. Either you go to individual structural member property and assign it from here, or directly select the structural member and click on assign shell stiffness modifiers, and you can assign the modifiers from here. But since we are only to assign the property modifiers for the slab and drop panel, so we can do it easily from here. I'll be selecting the bending property modifiers as well as the membrane, as recommended by ACI code to use 25% of the gross moment of inertia. And similarly for the drop panel. Since ETABS work on direct design method which utilizes the design strips. So there are two strips, the middle strip and the column strip. The column strip width is quarter of the clear span in the shorter direction. In our case we have both these spans of 24 feet. Hence, the width of the column strip is equals to 24 feet divided by 4 is equals to 6 feet in each span. Let's start drawing the column strip. Make sure to select the column strip from here. 72 inches is equals to 6 feet. So there are already strips assigned when we started with the template of the structure. But let's for time being erase these strips and reassign them, so you get the idea of how they are actually assigned. So I am pressing delete button to delete the strip simply and restore the object visibility. So let's go to design strip, strip layer A for this direction, for the longer direction. 72 inches to the left means 72 inches in this span, and 72 inches to the right means in this span. Click on show width to see the width of the strips. Always draw strips from top to bottom and left to right. In strip layer B, we'll be drawing from left to right. So first drawing the column strips. The column strips passes through the columns, covering the quarter of the span on each side. Now in the last part, we only have to have the strip in the left side. We are going to undo it and draw it from here. Now the remaining width will be of middle strip. So the middle strip will be 24 feet minus 6 minus 6. 6 feet of column strip from here, and from here 6 feet. So the remainder will be middle strip. We are getting a 12 feet wide middle strip. But since the middle strip is also drawn in two parts, so we will be dividing it by 2 to get 6 feet. Let's click on middle strip. So we'll need to turn off the snap in order to catch the midpoint from the beam. So we draw the middle strip, 6 feet on the left, 6 feet on the right. Similarly in the vertical direction in all spans. Now let's start with the direction B and with column strip. In order to easily draw the strips, let's turn off the visibility of layer A. If you mistakenly draw the strip out of the slab, click on undo from here. Now similarly select the middle strip from the center for the layer B. Click on undo as we didn't select the middle strip. We have drawn the strips and the slabs and click on save the model. It is important that once you click on the strip and check the rebar material properties. You can also ignore the design or the post tensioning in the slip if you are designing the normal reinforced concrete. We can also override the live load reduction factor or reduce live load factor. You can also override it to middle strip or column strip and change the strip layer as well. You can also alter the geometry of the strip from here once the strip is drawn. Right now our strips are assigned OK from geometry perspective and material of the rebar. So we have pressed OK. Now go to the design preferences for the slab. You can specify the cover of the slab from top to bottom and preferred bar size as well. Inner layer bar is layer B. If the shorter dimension is B, then it would be the main bar. The short bar or the shorter span bar is always the main bar, but here both the spans are same. So it doesn't matter whether here it be A or B. This is important when we are using the pre-stressing. Right now we are not doing pre-stressing. You can also select the design code from here. It is selected ACI 31814. Now select the slab and design. View revised flexure overrides, or select the strips and click on view revised flexure overrides strip based. You can all override here just in a single click, but right now our properties are assigned as according to the design criteria. Similarly, you can select the stories for the design. Right now we are selecting the story 1. But before starting the design of the structure, we need to run the analysis. Click on run analysis. We have set the shortcuts, or just go to design, start design for the selected stories, as we selected the story 1 for the design. Okay, so important part here is it is showing the status for what actually design is being shown. Strip design layer A, top bottom reinforcement. But before that we need to check the deflection of the slab. Let's turn off visibility of the strips first and check the deflection for verifying the thickness of the slab. Long-term deflection limits verifies the thickness of the slabs. According to ACI code, the long-term deflection is to be checked by shorter span divided by 240. The maximum allowable deflection due to combination of live load and dead loads is equals to 1.2 inches in our case. The 24 here is the span in feet multiplied by 12 to give it in inches divided by 240 of the formula. The combinations for long-term deflection can be conservatively taken as 3 times sustained load plus 1.5 times movable or temporary loads, or in simple words 3 times dead load plus 1.5 times live loads. Let's define it in ETABS. You can define the load combinations without unlocking the model. I'll be adding all the dead loads finishes load, parapet load are also included in the dead load. So now dead loads are finished. Dead, finishes and wall were dead loads. Now we have the live load left. So we'll be giving a multiplier of dead load as 3 and 1.5 to the live loads. Now in order to check the long-term deflection, draw contours on the object and displacement uz in direction of z-axis. The z-axis is perpendicular to the slab. The scale also shows the deflection points. The deflection limit for us was 1.2 inches. But here we are getting about a higher deflection. So we need to increase the slab thickness, or you can increase the concrete strength. But increasing the slab thickness has a direct effect on controlling the deflection. So we are getting a maximum thickness of about 3.5 inches. While the limit we calculated is 1.2 inches. So let's unlock the model and revise the thickness. I'll directly be proceeding to slab thickness of 10 inches. But since we revised the slab thickness as 10 inches and we already discussed that the drop panel should be at least slab thickness divided by 4. So we'll be revising the drop panel thickness again. So the thickness of the drop panel is to be revised considering the increased slab thickness as 10 inches. Gives us 2.5 inches as minimum drop panel thickness. Let's say it has 3 inches considering a round up. So the total drop panel thickness is equals to slab thickness plus drop is equals to 13 inches. Let's apply it in ETABS. Since we created a copy of the section, so the modifiers will already be assigned. The limit for deflection is 1.2 inches, while we are getting almost twice of the limit, that is 2.4 inches. So I'll unlock the model and try to make the slab thickness as 14 inches. I'll be changing the slab property from the right click menu. And since the drop is supposed to be at least quarter of the slab thickness. Since the slab thickness is revised to 14 inches, so dividing the 14 inches by 4 we get 3.5 inches. Let's take the drop panel thickness as 18 inches. Let's rerun the model. Basically, if we had the liberty to change the drop or flat slab system to beam slab system, then the deflections would have been controlled, as there is high loading on the floor consisting of finishes and the slab self weight, as well as the masonry load which we previously defined and applied on the structure, and the forces of the earthquake in the structure are of high seismic category. But important thing to note is when we are increasing the slab thickness, the dead load on the slab is also increasing, which in other words also increase a deflection on the slab. Since we are using a very conservative load combination for the deflection, that is 3 times dead plus 1.5 times live, so it gives a bit higher deflection than actual. For the deflection actual requirement, we need to perform a non-linear analysis for the deflection, which is possible considering the cracked moment of inertia in CSI SAFE. But ETABS has limited option, it calculates only the linear deflection for slabs. The version I am using is CSI ETABS 2016. Let's check the slab thickness. And deflection. So finally we are meeting the deflection requirements utilizing a slab thickness of 14 inches. The maximum deflection comes out to be 1.13 inches, which is less than the 1.2 inches limitation. Now next we are going to check is the drop panel thickness, whether it's sufficient to resist the punching shear. So we'll click on design of the concrete slab. Go to design, concrete slab design, and display punching check. So the NC means where the punching check is not applicable or compliant. As you are seeing the beams here, so the punching is not possible where there are beams, but the punching is definitely possible where there are drop panels and slabs resting on the columns directly. So the ratio must be always less than 1. You can always check the requirements as clicking on the center point and the punching properties appears. The column punching check shows the parameters utilized in calculation of the punching shear, including the moment ultimate utilized, maximum stress, punching shear ratio, as well as the drop panel punching check. The higher punching shear ratio is displayed in ETABS, as 0.304 is the higher value covering the column punching check. This ratio, I repeat, must always be less than 1. In our case, all the columns are not punching in, none of the column is punching in the drop panel. So we are okay with the drop panel thickness and the slab thickness as well as the deflection criteria. Now let's proceed with the reinforcement. Click on design, concrete slab design, display flexural design. First of all, click on impose minimum reinforcing according to the code you have selected. Let's start checking the design from the top rebar. Number of bars, let's say we select number 3 bars to check our design. Click on apply. So we are getting the, if you see on this bottom left corner, when I hover the cursor over the particular reinforcement, you can see the width here. It means that since here it is written 333 number 3 bars for top reinforcement, in this direction we are required. So that means in a width of 12 feet, we are required 33 number 3 bars for top. Similarly, near the drop panel, we are requiring a higher number of bars, that is 62 bars for a width of 12 feet. 62 bars to be distributed in 12 feet. And here we are getting a bit more higher, that is 77 bars to be distributed in a width of 12 feet. 12 feet, I repeat, we are getting the distance. As you see on the bottom left of the screen, width is equals to 12 feet. So this means 77 bars are to be distributed on a width of 12 feet. So I guess the 77 number is the highest. We can further check it here, placing number 3 bars at 6 inches. If these all bars vanish, then we are okay with design. Basically, dividing 77 with 12 gives us the number of bars per foot. 77 bars in 12 feet are needed, and the number here we are getting means that we are requiring 6 bars per feet. So that is a very high number of bars. So we can increase the diameter of the bar to number 4. So we are getting a lesser number of bars. Let's click on here. We are to revise the top mesh until these extra bars vanish. You can always place the extra bars in the drop panel as well, but since I prefer to continuously provide the mesh, so it's easier to execute on the site. So I'm getting a top bar of number 4 at 4 inches with approximately few extra bars on some of the spans. Since it is a large slab, we can even go to number 5 bars and increase the spacing as well to be economical. Let's try 6 inches spacing. So number 5 at 5 inches is working for top bars in vertical direction. Let's check on horizontal direction. In horizontal direction, we are getting few extra bars. Let's try number 3 bars. This is very less number of bars requiring. One number 2 bar doesn't make any sense, so we can ignore these bars. So the top bars on the whole slab, we are requiring number 5 at 5 inch center to center. This is a typical uniform mesh of top reinforcement we are utilizing, and these are the extra bars. So utilizing a mesh of number 5 at 5 inch center to center for top reinforcement doesn't require any extra rebar. So I'll be drawing it in the AutoCAD. The dashed line shows the top reinforcement of the slab. For top reinforcement in both directions, we require Now let's proceed with the design of bottom reinforcement and with layer A. Reducing the thickness of the bottom mesh. Let's try number 4. Utilizing a bottom mesh of number 4 bar at 7 in center to center, not require any extra bars. We can further economize it by using a higher spacing, so we are not really getting very high bars in the bottom mesh. We have also checked the bottom rebar for layer B, so there is no extra bar required after providing a mesh of number 4 at 7 inches. So number 4 bars are working in both direction for the bottom mesh. Similarly in the other direction. But since the drop panel is hanging below the slab, we need to provide bars here as well. We'll be utilizing a same mesh utilized here at the drop for the drop steel. If you think that the top mesh is quite over designed, so we can always revise the top mesh. The top mesh consists of the number 5 bars at 5 inch center to center in both directions, that is long direction and short direction. But in this case we have long direction and short direction equal, so we can further reduce the top mesh size if you want to by providing extra bars. Now let's go back to top rebar and try making the design economical. Number 5 at 8 inches gives me a lot of extra bars if I am providing a mesh of number 5 at 8 inches, or let's try number 5 at 7 inches. So utilizing a mesh of number 5 at 7 inches instead of number 5 at 5 inches, I have reduced the bars in the drop panels in the overall slab. So you can increase this. In other words, I am making the slab design economical by help of extra bars to be. We have marked the bottom bars in the drop panels, but now we are requiring the extra top bars in the drop panel as well. So for demonstration purposes, I'll be drawing the extra bar for only one drop panel. I take the bar and make it 1.5 times. Since the top bars are always shown as hidden in the drawings, So in both directions I'll be providing the top extra bar in order to save extra amount of steel we provided previously in the mesh. So I'll be selecting both of the layers. And conservatively, for time being, only for demonstration purposes, I'll be going with the highest number. Actually, we are mistakenly using number 2 bar here. So let's utilize a higher number of bar, that is number 7. So we are getting 5 number 7 bars in this direction, and for the other direction we are getting 4 number 7 bars. This is how we designed the slab with drop panels and considered the economical design.